Hello and welcome back. In this video, we're going to be taking a look at the concept identification for concepts in the AP Physics 2 course. In the left-hand column, you're going to see given prompts or possible, these are phrases of possible AP exam question scenarios that have been essentially seen in the 5 years of AP Exam 2 testing. We're going to try and draw a sketch of these so we can get a visualization of this, and we're going to relate this to any and all concepts and the relevant formulas that would go with them. Let's take a look. What if we have something for, in the case of number 1, what if we have something that is being submerged or floating in a fluid? So I'm going to break this box in two, and let's say we have situation where we had something floating, or it could be something that's either rising or sinking in the fluid, either one. But in either case, you have to know that the weight of the fluid again, or the weight of the object still goes down, and the buoyant force still goes up. And that's true in both cases. Weight goes down, buoyant force goes up. Well, the concept would be that of buoyancy. This is a buoyancy concept. But it's also a Newton's first law concept when there's no acceleration, and it's a Newton's second law concept when there is. The formulas we would need with this are buoyancy equals rho of the fluid times V times G. The Newton's first law equation is, of course, forces going up equal forces going down. And the Newton's second law equation is causing force minus opposing force equals ma. Number 2, what about a situation where we have a fluid, and let's say you are acknowledging or dealing with somehow in the problem a point that is submerged deep under this fluid. So some point P deep under the surface of the fluid. Well, that is a pressure at depth problem. And the way pressure at depth works is the total pressure at point P is the sum of atmospheric pressure, which is P naught, plus hydrostatic or water pressure, that's rho times G times H. Number 3. What if we have a force or a weight applied on a particular area? Okay, well, to visualize this, let me just really quickly draw a cube, just so I can give some sort of geometric reference. And let's say we're applying a force on, one face of that cube. That, ladies and gentlemen, is just a plain old pressure problem. And pressure is the force per unit area. Number 4 gets into actual fluid flow dynamics. So let's say we have 2 different diameter of pipes. Diameter 1 and diameter 2. And the volume flow rate essentially ends up being exactly the same. Now, the concept is referred to as continuity. Okay, but what it means is constant volume flow rate. Okay, it'd be helpful for you to know that flow rate is the cross-sectional area times the velocity, or it's the volume, right, per unit time. But usually we're going to focus on the part of the fluid flow rate that has to do with the conservation of fluid flow rate, meaning area 1 times velocity 1 equals cross-sectional area 2 times velocity 2. Well, in number 5, what happens if all of a sudden we look at the fluid working up against gravity? So let's say we have a pipe and we're going uphill like this, and maybe it changes diameter, maybe it doesn't. That part's, that's using this concept in conjunction with continuity. But let's say it's some height above the lowest point, right? This is an example of a Bernoulli's principle problem. Bernoulli's principle is a way to essentially analyze the energy of a fluid, because Bernoulli's principle is really just conservation of energy applied to pressure at different points. So P1, pressure 1, and let's call this region 1 here and region 2 over here, is equal to the kinetic energy of the flow rate. And so instead of 1/2 mv squared, it's 1/2 density v squared, plus, instead of mgh, it's density rho gh, 1 and 1. And that's going to equal P2 plus 1/2 rho v2 squared plus rho gh2. Well, in number 6, we have a situation where we have different masses that are at different temperatures, but are all somehow all in contact with each other so as to allow for heat to transfer between the two objects. So let's say this is object 1 and object 2, and we'll say object 3 is way over here. And they're all at different temperatures. They're at different temperatures and they're somehow in contact, then heat is always going to flow from the higher temperature object to the lower temperature object. This is known as thermal equilibrium. It's also known as the 0th law of thermodynamics. No real formula per se, other than to understand the dynamics of heat flow. When objects reach thermal equilibrium, heat does no longer flow between the objects. Now, what if we have mass and volume given? Well, that might be a situation where you don't necessarily have a picture, really don't even need a picture for that matter, but that's an example of a density problem. And density is mass per unit volume. But as we saw many times in the unit, mass can be written in terms of density times volume. Now in number 8, what if we have a situation where we have two oppositely charged plates separated by a distance? So let's draw, a negatively charged plate and a positively charged plate, separated by some distance d. This could be a variety of different formulas and a variety of different concepts. Number 1, this could be an electric field problem. Electric field between parallel plates, that is. But it could also be in addition to electric potential between the plates, could also be conservation of energy if we release a charged particle between the plates because they will always accelerate. Positive charges accelerate with an electric field, negative charges against. And so we could either use the equation, the potential difference divided by the distance, which satisfies the connection between electric field and electric potential, and conservation of energy, in which case energy initial equals energy final. And that usually would end up being something like electric potential energy, charge times voltage, equals 1/2 times mass times little velocity squared. Now in number 9, let's say we had a capacitor Okay, so first we have a battery. Let's say we have a capacitor that's hooked up in a circuit, okay, and it has a voltage difference applied across it. And it's been turned on and storing charge for quite some time now. Well, that is an example of steady state capacitance. And we could use the formula capacitance is equal to epsilon naught times the area of the plate, the capacitor plate, divided by the distance between the plates. Or the charge stored on a capacitor is equal to the capacitance times the potential difference across. In number 10, what if we have a charge moved from infinity, some infinite point, to a point of determined potential? So let's say we have here's our number line, and way over infinitely far away, we have a charge that is being brought to point P. This is an electric potential problem. But, ladies and gentlemen, it's also a conservation of energy problem, in that the potential would be K times Q over R, but it would also be, in terms of conservation of energy, charge times the potential difference, that's the electric potential energy, and equals 1/2 times m times v, the velocity squared. In number 11, we have parallel charge plates and an electric field. Now, this is basically similar, if not the same, to what we experienced a few back in number 8. Same concepts really, and same formulas needed. Now in number 12, let's say we had 3 or 4 charges in a linear or rectangular arrangement. Okay, here's some samples. Maybe you have a number line, and on that number line you have charge 1, charge 2, charge 3. Okay, and maybe we're looking for the net force on charge 1, or charge 2, or charge 3. Or maybe we're looking for the net field at some isolated location. But sometimes we saw that they were also in two-dimensional arrangements too. For instance, you might have charges that are at four corners. Positive, negative, positive, negative, and maybe the charges reverse or change in such a way. These are examples involving net electric field, so total electric field at one particular point. And since electric field is a vector quantity, you're going to need vector components. Okay, and Pythagorean theorem is always needed when we're talking about a two-dimensional array. If we're talking about a one-dimensional or linear array of charges or fields, then that's as simple as adding or subtracting your fields to get the net field. In two dimensions, we need Pythagorean theorem. In addition to finding net field from problems like this, you are sometimes asked to find net electric force. And sometimes we're asked to find the net electric potential at a particular region. Every once in a while, potential energy. But these are the most common. Now, using this, of course, we would need the electric field formula, K Q over R squared. And we would need to find this for every single point required, and then, of course, Pythagorean theorem to get the net field. Once we have the net field, electric force is just simply a charge at a particular location where the net field is times that net field. And lastly, if we want to find electric potential, it's K times Q over R. The difference between these is that field and force, and by the way, sometimes force is also using Coulomb's law between this difference between two charges. Now, these two equations, we do not put the negative quantities inside the charge. So negative charges, we don't do it. We take the absolute value or the magnitude of the charge. Remember, negative charges and positive charges, their sole purpose is to figure out the direction of the electric force in the electric field, not the amount of force, not the amount of field. Potential is different. Potential is a scalar quantity. Okay, it doesn't point in any particular direction. Okay, in fact, it really leads to a change in potential energy. And potential energy is all about loss and gain, not about direction. So for negative charges, you do put in negative charges for and get negative potential as a result. Since potential is not a vector quantity, when you're finding net potential, you simply have to add all the potentials at one particular spot. Now, more specifically, what if we have two charges separated by a distance? Okay, so let's say we have a positive charge separated from a negative charge some distance r away. Well, this would be Coulomb's law, specifically. And Coulomb's law helps find the magnitude of the electric force between two charges separated by distance. And we use our Coulomb's law equation. Now, let's say we have, as number 14 suggests, a charge and a distance away. Well, now we're talking about two possible things that come to mind. Say we have a positive charge, and some distance r away, we have a point P. Well, there's two things we can find at point P. One, we can find the electric field at point P. Using KQ over R squared. Or we can find the electric potential. using V equals KQ over R. Now, if the question is specifically saying what will the speed be when you have a charge moved from some infinite distance away, that's an example of a conservation of energy problem. So we'll save that one for later. But it shares a similar resemblance to these problems. Now, in number 15, we're looking at a direct current circuit with capacitors all on the same path. So it would look something like this. There's the battery, there's C1, there's C2, and there's your path of current. Okay, all on the same path. This would be capacitance in series. And capacitors in series, we have two possible formulas that we can use for equivalent capacitance. 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus ... We can also say capacitors in series, CS is capacitors in series, would be the product of two capacitors, C1 times C2, over their sum, C1 plus C2, product over sum. Now this only works for two capacitors at a time. This is what is applied when you have two or more. Now, naturally, what typically has to be applied in problems involving capacitors is charge is equal to capacitance times the potential difference. Now in number 16, we're talking about a DC circuit where we have resistors on the same pathway. Remember, resistors have that zigzag symbol positive, negative. We'll call this resistor 1. We'll call this resistor 2. We can tell this is a series pathway because it's the same path. It's one path. And we're looking at resistance in series. And resistance in series is as simple as R1 plus R2 plus ... Just add them up. But in addition to that, typically we have to use the Ohm's law equation to find either the potential difference across a resistor or the current across any resistor. And so V equal I times R is often needed. Now how about we look at DC circuits that are on all different pathways? So we have capacitors on different pathways. Okay, this is a battery, not a capacitor. Notice there's uneven parallel lines. These are even parallel lines. So we'll call this C1, and we'll call that C2. This would be capacitance in parallel. And capacitance in parallel is just like resistors in series. So CP stands for capacitors in parallel, and we simply add them up. And yes, once again, Q is equal to C delta V is often needed. Now in number 18, we're having the same circuit, but this time we're looking at resistors on different pathways. Positive, negative, we'll call this resistor 1, and we'll call this resistor 2. This would be electrical resistance in parallel. The equation for it is very similar to current in series. So we have 1 over the resistance in parallel is equal to 1 over R1 plus 1 over R2 plus dot, dot, dot. Adding the inverses and taking the inverse of the answer. Or it could be the product of the two resistors divided by their sum. And yes, again, you'll need the Ohm's law equation. In number 19, we have a DC circuit with resistors in different combinations. So maybe we have a resistor here and two resistors like this, where you've got some in series, you've got parallel pathways, all of these are in series with that. So you'll have some combination of series and parallel together. Now, this would be resistance in series and parallel. Okay, Ohm's law is needed, and I really should have included that with 18 and with 16, since the Ohm's law equation is often needed. And we're going to need kind of a series of equations here. One, we're going to need this. We're going to need the equation for resistance in parallel. That's number one. We're going to need the equation for resistance in series. That's number two. And then we need Ohm's law. That's number three. And in number 20, we have a fully charged capacitor on the same path as a resistor. So maybe we have something like this, where you have a resistor on one pathway, and then a resistor and a capacitor on a completely separate pathway. This is known as an RC circuit. Okay, RC stands for resistor capacitor. And we're talking about fully charged means steady state capacitance would be the concept involved here. And we, of course, need to understand that steady state capacitance means that a fully charged capacitor acts like an open switch. No current through that part of the loop. Steady state capacitance. And from that, we need equivalent resistance formulas. We need Ohm's law. Okay, and we need the equation for charge across capacitor. In number 21, we have a fully charged capacitor, but this time it's on a different pathway, a parallel pathway. We could have resistor 1, a capacitor, and then resistor 2. Something I neglected to mention about number 20. Number 20 is specifically an RC circuit in series. Something to note about steady state capacitance. A fully charged capacitor acts like an open switch. thus eliminating current from this outer pathway, creating a very simple circuit with one resistor. Same concepts, only we are in parallel this time. And in this case, capacitance fully charged. Again, no current that way. We have ourselves a simple series circuit as a result. And of course, the same formulas apply as in number 20. Now, number 21, you have a current passing through a certain point at a certain time. And really, it should say charge passing through a certain point at a certain time. And that would be charge passing from point A to point B in some time interval. That is, of course, electric current. And electric current, by definition, is the flow rate of charge. So current is equal to Q over T. You could write T, you can write delta T. I even see people write little q over T. It honestly doesn't matter. Oftentimes, big Q was to establish a collective of charge larger than a singular charge, whereas little q is usually representing a point charge, something small, something minuscule, something almost fundamental, like an electron. Well, in number 23, we have a DC series circuit in series and parallel, but specifically the question is asking about ranking bulb brightness. So the first thing I would note, of course, is the nature of the circuit, right? It's a combination of series and parallel. That's number one. Which means if that's the case, then you should expect all these equations to apply. In addition to one more. In order to rank bulb brightness, we need to calculate the power, because electrical power is the indicator for bulb brightness, and power is current times voltage. All right, and number 24, what if we have a graph of current versus voltage, or current versus resistance? Now, it wouldn't be current versus resistance per se. If it was, okay, well, it could be. If you graphed current versus resistance, you'd get something like this. Current versus voltage would be very much a linear shape that way. If you graph current versus resistance, they are, of course, inverse related concepts. You'd get a graph that looks much like this. So in order to linearize that graph to produce a straight line, you have to since they're inverse concepts, you have to plot current versus the inverse of resistance. And when you do that, you do get a straight line. Okay, that's an Ohm's law concept, but it's an Ohm's law graph. Okay, and a couple things here. One, the slope is usually the inverse of the resistance, right? Or the slope, right, is the voltage. So the slope is going to be something. It's going to be something related to Ohm's law. Now, in number 25, we have situations where we have wires of varying thicknesses. So say we have a wire here, and let's say we have another wire that's just a bit wider, a bit thicker. Okay, this plays into the resistance of a conductor or the resistance of a wire. And the equation we need for that is R, the resistance, is equal to rho, the resistivity, times the length of the wire divided by the cross-sectional area. Now in number 26, we have a charged particle moving at some angle relative to a magnetic field. So let's say we had a magnetic field that was pointed this way, to the right. And let's say we had some charged particle moving at some speed this way right here, where this represents the angle between the motion and the field. There's two concepts that are going to come to mind when doing problems like this. One, this is the magnetic force. Magnetic force on a charge, on a moving charge. But it's also right-hand rule number one. RHR stands for right-hand rule. Right-hand rule number one is the one where we place our fingers in the direction of field. The tip of our pencil either comes out of the palm of our hand for positive charges or out of the knuckles of your hand for negative charges, and the thumb goes in the direction of the velocity or the motion. And the equation we need for this is F equals QVB sine theta. Now, something important to note, when, since theta is the angle between motion and field, that means if you're moving perpendicular to your field, perpendicular would be 90 degrees, sine of 90 is 1. So if the sine of 90 is 1, that means any particle moving perpendicular to field is just going to be QVB. All right, so let's say we have a charged particle moving with or against a field. And let's draw a field to the right. This time, let's put the charge going with or against the field. Same concepts. Same formula. But this is how it gets applied a little differently. Again, since theta is the angle between velocity and field, if you're going the same way the field is going, the angle between you is 0, and sine of 0 is 0. And 0 times QVB is a big 0. And what if we have a situation where we have a magnetic field and a charged particle stationary in that field? Well, magnetic force on a charged particle is the main concept, but you have to be a moving charge. That's why I've got this term here. Magnetic force on a moving charge. If you're not moving, use the same equation. F equals QVB sine theta. If velocity is 0, right, the whole force is 0. And in number 29, we have a charged particle, an electric field plates, charged particle, parallel plates, and an electric field established between the plates. So it's very similar to what we previously went over a little while back. Okay, so let's say we have a positive field, a positive charge. And let's say we have an electric field established from high potential to low potential, in this case downward. And let's say we placed a charged particle in the field. It would, of course, accelerate against the field. Positive charges accelerate with the field, negative charges accelerate against the field. And the possible concepts that would go with a scenario like this would, of course, be electric field. We need to know something about it. You need to know that this is a uniform electric field. So it doesn't matter where if the particle is here, 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 or right up against the plate. Anywhere in there, you're going to experience the same electric field. It's constant. Electric force is obviously a concept because force is charge times field. So field is the potential difference between the plates divided by the distance between the plates. Force is charge times field. And you also need Newton's second law occasionally. Causing force minus opposing force equals ma, as a charge accelerates from one plate to the other. Now in question 30, what if we experience an electric field and a magnetic field in the same region? Let's take a look. We can see the electric field is directed upward. Now, to have an electric field and a magnetic field in the same region, that serves the purpose of allowing a charged particle, say an electron, to pass through undeflected. Pass through in a straight line. Now, in order to pass through in a straight line, here's what has to happen. The electric force, which is pulling that electron down towards the positive plate, needs to balance the magnetic force. So let's say we had, let me just draw this in a different color. Let's say we had magnetic field going out of the page in the same region that the electric field is directed upward. Now you already know the electric field is pointing, the electric force, is pointing down. The electric field is pointing up, but the force is down. Force on a negative charge is opposite the field. So the electric force is down. In order to pass undeflected, the magnetic force has to be up. And if we use right-hand rule, that pretty much guarantees that. Your fingers are out of the page, your thumb is to the right, and the pencil sticking out of your knuckles, because it's a negative charge, goes towards the top of the page, towards the negative plate. Therefore, your magnetic force going up balances your electric force going down. Magnetic force from the magnetic field balances the electric force from the electric field. It's important to note that the In order to do this, accomplish this, the magnetic field and the electric field must be perpendicular to each other. This is referred to as a velocity selector. Sometimes they're referred to as cathode ray tubes, CRTs. Cathode ray tubes are, of course, the big, huge electron guns that were found in the back of old TV sets. And the way to reason this one out, of course, is electric force balances magnetic force. Therefore, QE balances QVB. Since the charge is the same, E is equal to VB, or the velocity is the electric field divided by the magnetic field. So now in number 31, we have a charged particle that's curving in a magnetic field. So let's pretend that we have a magnetic field directed, let's say, into the page. And let's say we have a positively charged particle entering the field right here at this point. If we use right-hand rule at that point, what we find is our fingers go into the page, our thumb is directed right, and our pencil tip force is pointing in this direction right here. So that naturally curves the path, just like this. Now at this location, same thing. Fingers into the page, thumb is now directed up, because up is now the new direction of velocity, and our force is directed this way. Again, curving the path in a semicircle. This concept is dealing with magnetic forces on a moving charge. The key word there being moving. But this is also a case where we absolutely need to know how to do right-hand rule number 1. Now, our formula for it, although is QVB sine theta, you won't need the sine theta for problems like this. If you're curving in that magnetic field, chances are, majority of the time, you're going perpendicular to your field, which means the motion perpendicular to the field means theta is 90 degrees. Sine of 90 is 1, and this becomes just QVB. So I'm going to shorten it. And then the last thing we need, of course, is the idea that a magnetic force is a centripetal force. And so you have to be able to do the following. You have to be able to derive this. Magnetic force is QVB. Centripetal force is mv squared over r. You can see one factor of v cancels, and if I solve for r is equal to q times b over m times v. Other way around, sorry. M times v over q times b. And from this, we can see the faster you're going, the bigger the radius of curvature. The more massive you are, the bigger radius of curvature. The greater the charge, bigger charges, smaller radius of curvature. Stronger field, smaller radius of curvature. Now, in number 32, we have a situation where we have some point away from a current carrying wire. So say we have a current carrying wire, okay, and we're passing electric current, let's say in this direction here. Now that's going to produce a magnetic field that wraps around it. magnetic field would go into the page below the wire, and it would go out of the page above the wire. And let's say we're talking about some point P way off up over here. We're talking about magnetic fields specifically around a wire, magnetic field around a current carrying wire. And the specific equation that matches with this concept is mu naught times I over 2 pi r, where really the magnetic field relates to the amount of current, greater field strength, farther away, weaker field strength, right? And those are really the only two variables involved, as mu naught is known as the magnetic permeability. It's a constant of 4 pi times 10 to the negative 7. Well, in question 33, we have a situation where we have two parallel wires, kind of like this, some distance apart. Maybe the current is either going the same way or it's going opposite way. This would be the magnetic force between two current carrying wires. Between two wires. And we're essentially going to be using the equation F equals BIL, and we're going to be substituting this for B. And we do that, we get F is equal to mu naught I1 times I2 times L all over 2 times pi times D, where R represents the distance away from the current carrying wire. This is the distance away from one current carrying wire to the other, which means essentially the distance between the wires. In question 34, we have magnetic field lines passing through a loop or a solenoid. Okay, so let's draw a solenoid. Let's say we had a battery hooked up like this, and it makes that shape. And so the way we could visualize this, of course, is the electric current goes from positive to negative. Electric current would go up, over, it would go towards the back. And you can see every time it would go over the top towards the back. Now, in order to do this, you're using the magnetic field of a solenoid and right-hand rule number 2. And in this particular case, what we would do is we would put our thumb over the top. This means into the page. And your fingers would wrap around in a direction that looks like this. In other words, through each loop, through each one of these loops right here, you'd get a magnetic field that's passing this way, this way, this way, this way, this way. So the collective field is passing, in this case, through the loop, through the solenoid, to the left. If the current reversed directions, then the magnetic field would reverse directions. Okay, and the equation we use for it is mu naught times I times n, the number of loops, divided by the length of the solenoid itself. Okay. Let's say we have a loop entering or exiting a magnetic field, or rotating in a magnetic field, or a magnetic field changing strength within a loop. Any of those are possible. So let's draw a few field lines directed into the page. Let's say we have a loop that we are forcing into this field right here. Bringing it in this way. As we do that, we're going to be dealing with the following concepts. One, we're dealing with Faraday's law. Two, you're dealing with the concept of magnetic flux. Three, we're dealing with Lenz's law. Okay, what is Faraday's law? Faraday's law states that the induced EMF is equal to the rate of change of flux, where phi is the symbol for flux, so it's the rate of change of flux. Don't be surprised if you saw a flux time graph. The slope of a flux time graph would be what? It would be the induced EMF. Even though I've never seen a graph like that, you have to be thinking ahead. Rise, overrun. And then a little n in front to indicate the number of loops. Usually it's just one loop. Now you also need the equation for flux itself, which is field times area times the cosine of the angle. Where angle here, angle theta, is the angle between the area vector and the field vector. Now, we talked about this in class. The area vector is not truly an area vector per se. It's really the normal from the plane of the area. Okay, so it's really the normal vector. So the theta is the difference between where the field is directed and the normal to the plane of the loop. Something to note, if a field passes perpendicular to a particular area, such as what you're seeing here, or let's say you had a loop like this, and instead of passing at an angle, where this is our angle theta here, let's say we were passing perpendicular into the loop. Well, then what would happen at this point? Theta would be 0, and cosine of 0 would be 1, which means this oftentimes simplifies to b times a when the field is perpendicular to the loop. Now in number 36, we have a rail gun situation. Now in a rail gun, you've got two rails and we have, it can either be a resistor over on the left side or just a completed part of the loop. Oftentimes I see a resistor over on this side. And then we have a bar placed over the rails. Now the two rails themselves are usually, this is one rail, this is another rail. The two rails themselves are usually immersed in some magnetic field, kind of like I'm showing you here. Now, what you typically see in problems like this is the rail itself, and this is the distance L across. The rail itself is usually forced in some direction, either towards the resistor or away from it. So it could be forced like this. Now, if it's forced like this, you can see the loop that's being made. There's a loop. There's a circuit that's being made right here because the actual bar that passes over the rails completes the circuit. Now, if I pull the bar closer this way, you can see there's fewer field lines passing through that loop, which means the flux got smaller, right? Or I could pull it the other way, in case the flux is getting bigger. So by pushing or pulling that bar in one direction to the other, you're getting a situation of induced EMF. So it's a specialized form of Faraday's law, and it's referred to as motional EMF. And the equation that gets derived from Faraday's law is the induced EMF is equal to the field times the length between the side rails times the velocity of the bar as it's moving. Now 37 deals with light bending as it passes through a prism. So let's imagine a triangular prism. Okay, and we get white light passing into one side. It will bend a little bit here, and as it comes out the other side, it's going to bend again into specific colors of the rainbow. Red, orange, yellow, green, blue, violet. This is known as dispersion. Dispersion is the spreading out of the different frequencies of color using Snell's law of refraction. So it's a refraction problem. But it is specifically being spread out into the colors of the rainbow. N1 sine theta 1 equals N2 sine theta 2. Now in question 38, we have a case where light is passing from a material, a medium of higher optical density, to a medium of lower optical density. For instance, light passing from plastic into air or glass into air. I'm going to put the region of higher optical density up one, and then we'll make this N1. N1 is the index of refraction of medium 1. N2 is the index of refraction for medium 2. And in this case, N1 is greater than N2, according to this scenario. Now, if that's true, then light is going to meet the surface at this point right here. This is our angle of incidence, and it's going to refract far from that normal. This is, of course, a Snell's law or a refraction problem. Now, when you do any refraction problems, you have to be prepared with the following equations. One, of course, would be Snell's law. N1 sine theta 1 equals N2 sine theta 2. Let me write it like that. There we go. That looks better. But we also need to be able to find the index of refraction at times 2. In which case n is equal to the ratio of speeds, the speed of light in a vacuum to the speed of light in a medium, or the ratio of wavelengths, the wavelength in a vacuum to the wavelength of light in a medium. Now in 39, we have a mirror that's curving towards an object. So the object is going to be represented by an upright arrow. Let's say we have a mirror that's curving towards an object like this. Well, this would be a concave mirror. sometimes the concept of magnification will come up as well. The equations we need for problems like this would be the focal point, or the focal length, is half the radius of curvature. We need to know that 1 over the focal length is 1 over the object distance plus 1 over the image distance. And we also need to know that magnification is the ratio of image height to object height, or the negative of image distance to object distance. So SI over SO. Well, in question 40, we have a spherical mirror that's now curving away from the object. Well, same concept, really, but this one would be a convex mirror. Something to note about concave mirrors: the focal length is in front of the mirror, and the focal length when you're doing calculations is positive. In a concave mirror situation, the focal length is now on the far side of the mirror because the curvature is away from the mirror, which means now the focal point is going to be negative. So focal length is positive for concave mirrors. It's negative for convex mirrors. But the formulas are identical. Let's say in number 41, we have a lens that is convex on both sides. So again, you've got your object. This is referred to as the principal axis. And let's say you have a lens that's convex on both sides. This is referred to as a biconvex lens or converging lens. Now, it's called a converging lens for the following reason. And yes, magnification is still the issue with all mirrors and all lenses. But why is it called a converging lens? Well, it's because if we have parallel rays of light, lenses have two focal points, one on either side. And if we have parallel rays of light, they're going to all converge through that far side focal point. And it doesn't matter if the rays of light are coming from the left or from the right. And again, we're using the same mirror lens equation and same equation for magnification. Well, in number 42, we have a thin lens that is now concave on both sides. So, similar situation. However, the lens would look more like this. This would be known as a biconcave lens or a diverging lens. And again, yes, magnification is still a concept with all lenses and mirrors. Now, why is it called a diverging lens? Well, again, if we have parallel rays of light coming up or coming parallel to the principal axis, they're going to spread apart at angles like this. And they do so because their back rays extend through that focal point. And the same thing is true, of course, on the far side. And again, what's nice about all lenses and mirrors is we get to use the same three formulas. Now, let's say we're given or asked to find the image or object height. Well, that could be a situation where you could be given anything. You could be given a concave mirror. You could be given a convex mirror. I mean, you could be given a converging lens, or you could be given a diverging lens. It honestly doesn't matter. Okay? Any spherical mirror or lens. Okay, and yes, magnification is still involved in problems like this. Magnification has to be involved in a calculation like this specifically because, and yes, I'm going to reference the other equations too. However, I'm going to put a star next to the magnification one because you can see it's the only one that involves the ratio of height, image height to object height. So that's probably one of the more important ones. And that was for number 43. Well, in 44, we have a really interesting situation where we have what is called diffraction grating, which is basically microscopic picket fences that allow light to pass through and bend as they do it. But different kind of bending. So instead of bending as you pass through a different substance like refraction, now imagine bending around a boundary that's in the way. This would be called diffraction. So let's say we have one barrier, another barrier, and a third barrier. And you can see two slits have been created there. Now, what I'm going to do is I'm going to draw a few wave fronts coming into there we go. So we have a few wave fronts that are coming into this these boundaries here, and as they do, when a wave approaches a boundary, say this is the boundary here and this is a wave front, what the wave is going to do is the wave is essentially going to bend around the boundary like that. And so since you have a boundary here and a boundary here, it's going to bend twice. It's not just going to bend in this direction, it's going to bend in this direction too. It creates an arc or a semicircle. Okay, and so let's examine what that might look like. And over here, same is true. And you can see how the blue wave and the gray wave are essentially overlapping each other. They are what's called interfering with each other. Now, if I drew more, you'd be able to see it more. So I'll draw a few more just to make it a little more obvious. That, and then I'll draw some over here. Okay, and what we see here, and I'm going to highlight this in yellow, is where the gray and the blue intersect each other. You can see they're intersecting all the way up the middle. They're intersecting all the way over here. They're intersecting all the way this way. They're intersecting all the way this way, all the way that way. And if you were to follow these points of intersection, of course, are referring to the interference of waves. When they interfere at that location, they are constructively interfering with each other. Now, what does it mean for constructive interference? Well, that means light interfering with light constructively interferes to make a brighter light. This works really well, of course, with laser light, which is coherent monochromatic light, meaning one color, and you're you're going to have regions of very bright light. So let's say we set up a screen or a wall over here. You're going to have a region of bright light, a region of bright light, bright light, bright light, bright light, bright light, separated by dark, separated by no light in between. And this interference pattern is known as double slit interference, or Young's double slit experiment. But double slit interference is the concept. There are a couple of variables we need to know. X is the distance between adjacent bright regions. They're called fringes, bright fringes. L represents the distance from the double slit. You can see there's double slits, one slit, two slit. That's why it's called double slit. The distance between the slits and the screen where you're projecting the interference pattern on is distance L. And so if we look at the equation that matches this, X, the distance between bright fringes, is directly related to the wavelength of light and the length to the screen, but inversely related to the distance between the slits. So the distance between the slits is this right here. That would be distance D, how far the slits are apart. And M represents other integer multiples of adjacent bright fringes. So M equals 0 would be for the central bright fringe. I'll put this right over here. M equals 1 would be for the next one. M equals 2 would be for the next one. M equals 3, and so on. It's increasing integer multiples. Okay. Dark fringes work the same way, but the dark fringes are the ones in between, the non-lit up portions. And they're on, instead of every wavelength, they're every half a wavelength. So M lambda over 2, L over D. Now, you could also relate this as D sine theta equals M lambda. And if you were to relate a picture, let's say you have the two slits, and this is the distance L to your screen, and this is one bright fringe right here, and this is another one way up here. This is the distance between one wave, and this is the distance from the other wave. And if we zeroed in on this, that's perpendicular. This is D. Right there is theta, which makes that little sliver that I'm coloring in blue right there, that is our D sine theta. And it's literally equal to a certain multiple of wavelength. To the first bright fringe, it's one wavelength of difference between this pathway and this pathway. To the second bright fringe, it's two wavelengths of difference. So a certain integer multiple of wavelengths differentiates the paths and creates this little tiny difference called D sine theta. This again is known as double slit interference. Now in 45, we have a thin layer of plastic or oil or air that's sandwiched in between other transparent materials. Okay, so what we have there is we have medium 1, I'll call this N1, a very thin film, and then N2. So, for example, this could be air, soap in a soap bubble, and air. If you ever looked at a soap bubble, A soap bubble is nothing more than air on one side, air on the inside, and the soap itself makes up a very thin film for the spherical bubble. So that would be one example of a thin film. Or we could have air on top of an oil slick on top of water. This is probably one of the more common examples that you see. Okay, now this is referred to as thin film interference. Now for thin film interference, we do need the index of refraction formula, which is lambda O over lambda N. We do need to know that if we have light incident on, and light will always be shown coming in perpendicular along the normal. It'll always be normal to your thin film. And what's going to happen is it's going to reflect in a couple ways. Off the top layer, it's going to reflect. And off the bottom layer, it's also going to reflect. Now, how these two match up with each other depends on whether you see a bright color or whether you see no color. You could see a bright color as part of a rainbow pattern on a thin film, or you could see absolutely no color at all. Again, this boils down to constructive and destructive interference. So 2t, the equation is 2t. That's 2 times the thickness of the film, because you have to go through the film once and then twice again. So 2 times the thickness of the film is equal to m, again a multiple of the wavelength. Usually m is going to be equal to 1, so I don't usually focus on it too much, times lambda n. Now, if we put this in, and let's say we rewrote this, lambda n is equal to lambda O times n, and so we would get 2 times the thickness equals m lambda O over n. And if you multiply both sides by n, we get another version of this equation. 2nt equals m lambda O. Okay, so why is this important? Okay, if you're given the wavelength in the medium, if you're given the wavelength in the thin film, then use this formula, because you're already in the thin film. If you're given the wavelength, the vacuum wavelength, the wavelength of light in air, then you have to use this particular part of the formula. Well, in number 46, we have, in this case, some combination of pressures, volumes, temperatures, and it's usually, it can be part of a picture. It could be part of a picture in terms of, you have a cylinder, and then you have some sort of movable piston that's going up or down, compressing the gas expanding, something to that nature. Or you could be given what's known as a pressure volume diagram. Where the pressure and the volume are changing at different points, and the temperature can be related at the vertices of these particular changes of state. Okay, now this is known as ideal gas law. And PV diagrams, pressure volume diagrams. Now, the equations that we need for this to be able to work a PV diagram or an ideal gas law problem would be PV equals nRT for actual pressure volumes and temperatures given. Now, if you're given relative changes in pressure, volume, and temperature, meaning the say you're given the fact that the temperature doubled or the volume cut in half, then we can simply just go pressure volume is proportional to temperature. This one is the quicker way to analyze a PV diagram. Now, what other equations might you need? Well, this is getting a little ahead of ourselves because we haven't really reviewed this in the video series yet, but you also need the first law of thermodynamics formula. You could also need, in order to solve a PV diagram, you could also need the heat transfer formula too. So we'll wait on that one. We'll wait to get to that one. So the main one, of course, would be those two right here. So I'm going to focus on those, not so much on first law. Now, what about in case of 47, where you have combinations of pressures, volumes, and temperatures changing states? Okay, again, you could have similar pictures going on, or maybe you don't have any picture at all. Maybe it's just telling this to you in words. But what you need to know is that this is ideal gas law between two different states, otherwise known as combined gas law. And combined gas law takes the idea of PV equals nRT at one pressure, volume, or temperature and relates it to PV equals nRT at another pressure, volume, and temperature. And so we end up with P1 times V1 over T1 equals P2 times V2 over T2. In question 48, we have heat and work related to a gas. Usually that's going to be some sort of cylinder and some movable piston that can either compress the gas or be expanded by the gas. And the concepts that come with this would be work on or by a gas, and the first law of thermodynamics. Now, work done on or by a gas depends on the point of view. So, for instance, work done by a gas is a positive pressure times a change in volume, whereas work done on a gas, let me rewrite this, whereas work done on a gas, this would be expanding by the gas or compression of the gas, is negative pressure times a change in volume. And the first law of thermodynamics is also written in two different ways. It is a statement of conservation of energy and is written as the change of internal energy is equal to the heat that you put into the system minus any work done by the gas, or the heat you put in the system plus any work done on the gas. Okay, now if we're again focused on, like we are in 49, gas changing its volume in a cylinder, well, that is pretty much specifically work done on or by a gas. And that would relate to these two equations here. Work done by a gas is pressure times the change in volume. Work done on a gas is negative pressure times the change in volume. Now in number 50, we have a situation where heat could be transferred between two objects. Now those objects could be gas and the walls of the container containing the gas. It could be two solids that are in contact with each other. It could be a liquid and a solid, or two liquids. It doesn't matter, but it's the heat transferred from a higher temperature to a lower temperature. So no necessary picture associated with this. It's just the heat transferred between two objects. Now, if we're talking about a liquid or a solid, then Q is equal to, Q being the heat transferred, is equal to mass times the specific heat capacity times the change in temperature. And this is specifically for liquids and solids. The heat transfer between liquids and solids, that is. But let's say we have gases under constant pressure. Well, instead of mass, it's going to be N, the number of moles, times the specific heat at a constant pressure times delta T. This is for constant pressure gas. And then lastly, Q equals NCV delta T. Well, that would be constant volume gas. In number 51, we're talking about heat taken in results in work getting done. So we're talking about work getting done as a result of heat entering a system that is a heat engine. Now, typically, the picture that's shown to represent a heat engine kind of looks like this. Now, this is not an actual engine, it's just a model of one. Okay, and you have an input side, heat from a high temperature source or a hot reservoir. You have useful energy, that's the work that's being done. And the other output you have is heat being released to a cold temperature environment or a cold reservoir. And so one concept would be work done by a heat engine. And the formula that goes with that is the heat entering the system minus the heat leaving the system. Q in minus Q out, or QH minus QC. The other one is heat engine efficiency. And that's represented by the letter E, and efficiency is a percentage. How efficient is the engine doing its job? Engines are designed to do work, right? So how efficient is the engine doing its job? How much percentage, basically, is the output work that of the total energy? Therefore, work divided by total energy, QH, is one equation. Your answers will be in the form of decimals, but they can be related to percentages. You could also rewrite this as 1 minus QC over QH. So you have two different versions of the same equation. Now in 52, we're talking about specifically maximum theoretical efficiency. Okay, now in this one, no real picture per se, but when you see the phrase maximum theoretical efficiency, we are talking about a Carnot engine. A Carnot engine is a maximum theoretical engine to essentially analyze the maximum potential that an engine could do its work, not what it will do. And the way that works is EC, the efficiency, the Carnot efficiency is the maximum theoretical efficiency. And it's E is just regular heat engine efficiency. This is Carnot efficiency, or maximum theoretical efficiency, and it's 1 minus TC over TH. Notice the difference. regular heat engine efficiency relates 1 minus how inefficient. So to talk about how efficient your engine is, it's 1 minus how inefficient your engine is. QC is the heat leaving the engine to a cold reservoir. It's the extra heat that's not needed from the system. So 1 minus the inefficiency would, of course, be the efficiency, right? Well, this is 1 minus the inefficient temperature, if you will. It's not really dealing with heat, it's dealing with temperature. Hence the theoretical nature of that particular form of efficiency. All right, now in scenario 53, we are now dealing with atomic physics. And in this one, we are given a situation where we have a frequency or a wavelength of light, a particle of light known as a photon, and it's being emitted or absorbed. So you might have a surface, and you might have some little particle, and it might be absorbed or it might be emitted. Absorbed means to take it in, emitted means to eject it, right? And this is the energy of a photon. Two equations that work for this: that the energy of a photon is directly proportional to the frequency. And so E is equal to H times F. Recall that the frequency is equal to C over lambda. Speed of light is frequency times wavelength. Therefore, if we replace frequency, we get E is equal to hc over lambda. We're going to use this one the most, where h is referred to as Planck's constant, 6.63 times 10 to the negative 34 joules second. Again, you don't need to memorize that number. You just need to know how to use it and plug it in. Now in question 54, we have certain frequencies of light that cause electrons to be ejected from a piece of metal. So what we have is we have a piece of metal, and you have light photons of a certain frequency, HF, certain energy, and thus a certain frequency. They're coming in, they hit, and it causes electrons to be ejected from the metal surface. This is a phenomenon known as the photoelectric effect. And there's really just one equation that we need, but we can write it two ways. The maximum kinetic energy can be written as the energy of the photon coming in minus the ionization energy of what's holding onto the electron in the first place, known as the work function phi. Now, again, you could also rewrite this as hc over lambda minus the work function. Okay, write that a couple ways. Now in 55, what if we are told or given something about the stopping potential, or it's something you're trying to find? Well, in a typical photoelectric cell, you might have a circuit, and you have a particular part of the circuit that is the collector of the electromagnetic radiation, and then emits electrons across the gap to essentially complete the circuit. And so the concept is still photoelectric effect, so you're still using photoelectric effect equations. But there's also another equation that would come to mind. So yes, K max is equal to HF minus the work function, but K max is also equal to the electron charge times the stopping voltage itself. And in number 56, if we have the nucleus of an atom and an electron that is orbiting that atom, it doesn't orbit in a perfect circle. Rather, it is found to orbit in strange wave-like properties. This is de Broglie wavelength. And the equation we use for that is lambda equals Planck's constant h over p. And of course, if you were to rewrite that, it would be h over mv. Now in scenario 57, if we are given an energy level diagram, and if we are, it looks something like this. You'll see several lines parallel to each other, spaced apart differently. And next to it, you'll see words like the ground state, n equals 1, n equals 2, n equals 3, n equals 4, and so on. So this represents the different states at which an electron can be excited to. It's excited to a particular state, and when it returns back to the ground state, it emits radiation proportional to the difference in the energy level. Okay, so these are known as atomic energy level diagrams. And the only real math involved, we do need the equation hc over lambda. Okay, we need that one quite a bit, where the value hc is a constant of 1240 electron volt nanometers. So we do need this formula to work it, but realistically, the other type of math we really need is just plain old good subtraction. In other words, the difference between energy levels is proportional to the energy that the electron emits as it falls back down to the ground state. In scenario 58, we are given a nuclear reaction. So let's say we have some isotope, we'll call it X, with an atomic number of A, or a mass number of A, and an atomic number of Z. And let's say it decays into something that has a helium nucleus. Now, that helium nucleus is known as an alpha particle. And this type of radioactive decay is called alpha decay. A helium nucleus has an atomic number of 2, an atomic mass of 4, and then of course the leftover isotope is going to be whatever this was, minus 4, and the atomic number is going to be whatever this was, minus 2. Meaning this plus this needs to add up to this, that would be conservation of mass, and this plus this needs to add up to this, that's conservation of electric charge. Total mass adds before and after, and total charge adds before and after. Now, multiple choice alpha decay problems typically look like this. If it's a free response problem, then chances are you are going to have slightly less mass than you started with. And so the Einstein's energy mass equivalent, where the change in energy is proportional to the mass difference times c squared. That equation is useful to account for the mass that was converted into energy. But for multiple choice questions, it's pretty straightforward in terms of making sure the mass is balanced and making sure the total charge balances. Again, where X and Y are hypothetical isotopes. So similarly, let's talk about a type of nuclear reaction in which an electron is ejected. Now, an electron is known as a beta particle. It's a fundamental particle, and this is known as beta decay. And so you have isotope X with atomic mass A and atomic number Z, and it decays into Y, okay, and it decays and it ejects in an alpha particle. So the a beta particle, excuse me, has no relative mass at all, so we're going to put 0 up there, and it has a -1 charge because electrons are negatively charged. Now you can see if this is 0, that means whatever the atomic mass is, that's going to be the same up here too. Okay, but it also means since this is a -1, this is going to be Z plus 1. You're going to add 1 to the process. And the way it works essentially is we don't always have electrons orbiting the nucleus. The neutrons that are in a nucleus actually break up into beta particles, which are these guys here, and protons. So one more proton actually adds to the protons that were already here, which is why the number increases. Okay, similarly, total mass needs to add before and after collision. Total charge, total atomic number needs to add before and after. I said collision, I meant nuclear reaction. Now in number 60 and 61 really don't have a picture associated with them, so I'm not going to focus on that so much. But in number 60, it says not knowing both the exact location and the speed of the electron. This is referred to as Heisenberg's uncertainty principle. And it means simply that. You can know about approximately where an electron is going to be in its orbit around a nucleus. You can approximate its speed at any one point in time, but you cannot know both simultaneously. That cannot happen. And so the relationship we can use with that is delta x, the position, times delta p, the momentum, which of course relates to the velocity. It's greater than or equal to h over 2 pi. That's the relationship. So you can either solve for this or this, but you cannot solve for both. Lastly, let's say we have a mass that's breaking down over time and releasing radiation in the process. Well, releasing this is a radioactive decay concept. A generic so specifically this is alpha decay and beta decay, but if we're talking about just a generic radioactive decay, we're not focused on what type of particle, we're focused on the overall mass and how it's decaying. We take the amount of substance N is equal to the original amount of substance at time equals 0, e to the negative lambda t.